Hi everyone, and welcome to this part of the playlist that accompanies Chapter 24 of the book Algorithms Illuminated, Part 4. This chapter is all about a detailed case study of our algorithmic toolbox for tackling NP-hard problems in action. So NP-hardness, it is not some purely academic concept. It really does govern your computationally feasible options when you're tackling a real-world problem. And so in these videos, we're going to see a recent illustration of the importance of NP-hardness in the context of a high-stakes economic problem, namely the reallocation of a scarce resource, specifically wireless spectrum. The solution deployed by the US government, something known as the FCC Incentive Auction, it actually employed an amazingly wide swath of the algorithmic toolbox, which you have just learned from this book or from this video playlist. So as we go through these videos and we learn about the details of the FCC Incentive Auction, I encourage you to pause on occasion and just to appreciate the journey that we've taken together through Algorithms Illuminated, which started way back at the beginning of Part 1 when we struggled through caret-pseudo multiplication and the merge sort algorithm. How what may have initially seemed like a cacophony of unconnected and mysterious tricks has now resolved into a symphony of interlocking algorithmic techniques. Before we get started, I should say that if you want to read more about the FCC Incentive Auction from its lead designers, namely Kevin Leighton Brown, who's a computer scientist at University of British Columbia, and Paul Milgram and Ilya Segal, both economists at Stanford University, I encourage you to dig into their paper, The Economics and Computer Science of Radio Spectrum Reallocation. And if you're interested more broadly in connections between economics and computer science, well, that happens to be one of my main research areas. And I wrote a book back in 2016 called 20 Lectures on Algorithmic Game Theory. So if that sounds intriguing to you, I encourage you to check it out. Let's begin by describing the motivation for the FCC Incentive Auction, which was to reallocate wireless spectrum. So a little history. So television spread like wildfire over the United States back in the 1950s. And in those early days, television programming was transmitted solely over the air by radio waves, sent from a station's transmitter and received by a television's antenna. Now, to coordinate stations' transmissions and prevent interference between them, the Federal Communications Commission, or FCC for short, divvied up the usable frequencies for broadcasting. And that's what's known as the spectrum, the usable frequencies. And they divided the spectrum into blocks called channels of 6 megahertz each. To prevent interference, naturally, different stations in the same city would then broadcast on different channels, using different frequencies, different colors of light. For example, what channel 14 actually means is the frequencies between 470 megahertz and 476 megahertz. Channel 15, the next block of 6 megahertz, so from 476 to 482 megahertz, and so on. Channels 14 and 15 are examples of what are called ultra-high frequency, or UHF channels. And they start with channel 14 at 470 megahertz, and they go up from there in 6 megahertz blocks. There's also the very high frequency, or VHF channels, and they occupy lower frequencies. So channels 713, they use frequencies from 174 to 216 megahertz, whereas meanwhile channels 2 to 6 use the frequencies from 54 to 88 megahertz. And if you do the math and you're like, oh, there's an extra 4 megahertz in that range from 54 to 88, well, that's for miscellaneous uses like, say, garage door openers. Back in the mid-20th century, television didn't have a lot of competition for spectrum, and so a big block of spectrum, lots of different frequencies, were reserved for over-the-air television broadcasting, also called terrestrial television broadcasting. But now fast forward to the 21st century, and you know what else travels by radio waves over the air? All the data exchanged between your mobile phone and the nearest base station. So for example, right now, speaking in the year 2020, if you're in the United States and you're using Verizon Wireless as your carrier, chances are you've been downloading data using frequencies between 746 and 756 megahertz, and uploading data using frequencies between 777 megahertz and 787 megahertz. You may notice that these numbers in the 700s, they're higher. So they're higher frequencies than the ones we were talking about for television channels, which were in the 600s and below. That's not an accident. To avoid interference, the part of the spectrum reserved for cellular data does not overlap with the part of the spectrum reserved for terrestrial or over-the-air television. Now, as you can imagine, mobile and wireless data usage has been exploding in the 21st century. And just in the last 5 years, like 2015 to 2020, it's increased by roughly an order of magnitude. Now, the more data you want to transmit, the more dedicated frequencies you need. And not every imaginable frequency, not every single color of light is useful for wireless communication. So, for example, if you have limited power, then very high frequencies will only carry signals for short distances. So the upshot is that spectrum is a scarce resource, and modern technology is as hungry for as much as it can get. Now, television, it's still a pretty big deal. Lots of people watch television, but terrestrial television, meaning broadcasting over the air, that is nowhere near as big as it was back in the mid-20th century. So in fact, roughly 85 to 90% of households in the United States rely exclusively on cable television, which of course, goes via cables and needs no over-the-air spectrum at all, or alternatively by satellite television, which uses much higher frequencies than typical wireless applications. So reserving the most valuable spectrum real estate for over-the-air television, that made sense in the mid-20th century, not so much in the early 21st. To reflect this shift in usage of spectrum over the past 70 or so years, as of this recording in mid-2020, a major reallocation of spectrum is nearing completion. So in fact, in the United States, after July 13th, 2020, there will no longer be any stations anywhere in the country broadcasting on what had been the highest channels. The channels between 38 and 51, corresponding to the frequencies from 614 to 698 megahertz. Every station that had been broadcasting on one of these 14 channels is either switching to a lower channel or ceasing all terrestrial transmissions, while possibly still broadcasting via cable and satellite television. Even some of the stations that were already broadcasting on channels below 38 are going off the air or migrating to different channels to make room for their comrades that are dropping down from channels 38 to 51. And all told, 175 television stations are relinquishing their broadcasting licenses and going off the air, while roughly 1,000 television stations are switching channels. Now, switching channels, it's not quite as big a deal as it may sound, because since the 2009 switchover from analog to exclusively digital broadcasting of terrestrial television, a switchover you may have heard about quite a bit in the news at the time. So since the 2009 switch to digital, the logical channel, meaning the channel that you see on a set-top box, that can be remapped to a physical channel different from the one historically associated with that channel number. So what that means is that stations that have their physical channel reassigned, they still get to keep their logical channel via this remapping. Clearing out these 14 channels 38 to 51, it liberated 84 megahertz of spectrum. So what's happened to it? Well, that spectrum has been reorganized and awarded to telecommunication companies like, say, T-Mobile, Dish, and Comcast, who are expected to use that new spectrum to build out a new generation of wireless networks in the coming years. T-Mobile, for example, as you've maybe already seen from their television commercials, has already flipped the switch on its new nationwide 5G network. Where there had previously been television channels 38 to 51, after a reorganization, there are now 7 independent pairs of 5 megahertz blocks. So that's what's denoted by the A, B, C, D, E, F, G in the bottom figure. So for example, the first pair of blocks comprises the frequencies from 617 to 622 megahertz. That's meant for downloading to a device, and then that's paired with a 5 megahertz block from 663 to 668 megahertz, which is then meant for uploading. And then the second paired block is just sort of shifted down by 5 megahertz. So 622 to 627 and 668 to 673, and so on for all 7 of those paired blocks. There's also an 11 megahertz duplex gap from 652 megahertz to 663 that separates the blocks meant for uploading and those meant for downloading. And then there's also at the sort of very left, at the very sort of bottom, a 3 megahertz guard band. So from 614 to 617 megahertz. That's to avoid interference with channel 37, which has long been reserved for radio astronomy and wireless medical telemetry. Now, this should all strike you as kind of a crazy, messy operation, right? There's so many questions to answer. So you had all these stations that were on the air before. Which of them should go off the air? How do you choose? For the ones that stay on the air, which of them should switch channels? And what should those new channels be? For the stations that go off the air and relinquish their licenses, what's the appropriate compensation for doing so? Then, after you've done this reorganization and you've created these 7 paired blocks, which telecommunication companies, are the lucky ones that get awarded them? And what should they have to pay for them? These were all questions that had to be answered by the FCC Incentive Auction, which was basically a big complex algorithm for doing the spectrum reallocation that leaned heavily on the toolbox for tackling NP-hard problems that have been described in this video playlist. Starting with the next video, we will talk about how this algorithm actually works. I'll see you there.